My last lecture, and it's now it's going to be a little more science fiction than the past 3 lectures. So in my last lectures, I told you about basics of supergravity, especially for the maximal extended theories, and I also told you about the emergence of hidden symmetries. And for the maximal supergravities, the result was that when you split the 11 space-time dimensions and view them from lower dimensions, so write this as d plus n, then the hidden symmetry, there appear the hidden symmetries of exceptional type, E, N, N as the hidden symmetries. Together with their maximal compact subgroups, which we denote as K of En. Now, one thing that's immediately obvious from this is that as you decrease the number of physical space-time dimensions, this n becomes bigger, and that means that the internal duality symmetry gets larger. So these duality symmetries are increased at the expense of space-time symmetries. Now, the case where this is still sort of completely under control is when we go to 3 dimensions, in which case the hidden symmetry is the E8 symmetry, and that's the maximal, the biggest among the 5 exceptional groups that were found by Killing and Cartan already more than 100 years ago. So today's subject will be what happens if we descend below this, because then you can of course simply extend this counting. And that was actually already conjectured in the early 80s by Bernard Juliard, who noticed that you could go down to 2 dimensions and then you get something called E9, and in 1 dimension you get something called E10. Now, because these are no longer in the list of in the group theory books, of course at that time people had to investigate what kind of groups are we talking about, but it turns out that since they're no longer finite dimensional, they must be infinite dimensional. So the basic result is that as n becomes bigger than 9, symmetries become infinite dimensional. So this is really carrying things to the extreme. When I said that the internal symmetries, duality symmetries, are increased at the expense of space-time symmetries, when you descend lower and lower, you reach the point when there's no more space-time left, or it becomes very trivial, but then you get a very huge symmetry. And this somehow embodies the idea that ultimately, maybe also in string theory, we should think of duality symmetries as being more important than space-time symmetries. So if there's any symmetry of M theory, if one ever succeeds in finding what that theory is, then we expect from this point of view that the symmetries will not be space-time symmetries of the ordinary type, but rather something like this. Now, you all know about the importance of these symmetries also in string theory, where they also conjecture to break down to the discrete subgroups. But what one has in string theory is sort of bits and pieces, and the question is there some overarching framework that could contain these symmetries and describe them, or contain, or encompass all these symmetries at the same time. Now, as I go down, of course, the first case is d equals 2, in which case you get something called E9. And this is still fairly well understood, and I will actually not say very much about it, because this is what's called the affine extension or loop group extension with a central charge of this symmetry, which appears in 3 dimensions. In fact, it's a very general phenomenon that if you start from 3 dimensions with a coset space and you descend from 3 to 2 dimensions, what you get is always the affine extension of the symmetry in 3 dimensions. And this turns out to be a generalization of the so-called Garrosh group, solution generating symmetry group of general relativity. So I assume that Gary will tell you everything about that. Gary, will you? No. Anyway, you were starting with Weil coordinates and so on. This is the framework to do this kind of. Anyway, as I said, we're doing science fiction today, so this is fairly well under control, at least from the group theory point of view. But we want now to go even further and decrease space-time dimension even more, and at the same time blow up the duality symmetry far beyond E9. Well, the E9 acts as a solution generating symmetry just the same way as it acts in general relativity. So you can start from empty space Minkowski solution, and with the Garrosh group you generate all kinds of axisymmetric stationary solutions of the type that Gary was talking about. So you can even put black holes on a string or make them rotate. So
right, normally solution generated transformations are symmetries of gravity, but not necessarily of a field theory.
well, here there are symmetries of the equations of motion they're really symmetries of the Einstein equations with in the axisymmetric stationary reduction or in the colliding plane wave reduction. Actually, this, as I said, I do not want to give a lecture on this because this case is even more interesting. Now, the first question you might ask here, of course, what?
One question. So, how comes that if you reduce it down to 3 or more, it's finite dimensional group, and suddenly it becomes infinite dimensional group?
Well, that's what I want to explain. I mean, here, yesterday I talked about, actually I'm losing time for things I didn't want to talk about. But anyway, I said here the scalar moduli space is a coset space G over K G. So that's the general structure that you always get. So it's G divided by the maximal compact subgroup. In higher dimensions, this is just a scalar manifold, or moduli space in more modern parlance. And here you can also think about this coset space in this way, but now it's infinite dimensional. Each point on the coset space corresponds to a particular solutions of the Einstein equations in this reduction. Anyway, so as I said, I don't want to go into this. This would be a separate lecture. The first question you might ask when you see this is that, well, let's do the reduction to one dimension, and then basically we're just left with the following fields. Let's say the reduction is on space-like killing vector, so we're just left with the time-dependent fields. Well, they're no longer fields, they're just functions. So you would say, well, question is why, how can this be terribly non-trivial? This is just a mechanical system with a one-dimensional kind of sigma model augmented by these three-form fields. But you have heavily reduced the number of degrees of freedom in this reduction. So how can you possibly get such a huge increase in the number of symmetries? And how can this symmetry then be realized in a non-trivial way? So that's the naive thing you might expect. However, that's not quite the whole story, because there are now two aspects to this which I would like to emphasize that show you how to go, that it goes far beyond this. And the first aspect here is the so-called BKL description or analysis of space-like singularities, or cosmological singularities. This is precisely Big Bang type singularity as it appears in cosmology. So let's just draw such a space-time. So here's the Big Bang hypersurface, proper time, and here we have world lines of freely falling observers that come out of this singularity. And then you can foliate this space-time by space-like hypersurfaces. So like this. And then there's something that's well known to cosmologists, it's so-called horizon problem. But actually this BKL analysis is long before horizon problem. They also noticed this fact but tried to exploit it in a different way. And the thing is simply that if you draw the light cones, the past light cones, which are somehow bent like this, it turns out, because there's a singularity here, so you cannot continue the space-time past this singularity, it turns out that these points here become spatially decoupled, which is precisely the horizon problem of inflationary cosmology. And now this was work they started doing in the late 60s, and the main paper is then 1972. This BKL stands for Belinsky, Khalatnikov, and Lifshitz, and you can even read about it in Landau-Lifshitz Volume 2, towards the end. This is where you never get to when you read this book, but at least I didn't get. At the time when I read Landau-Lifshitz, I never looked at these late chapters. Anyway, it's all there. So they said that in this, because you have this spatial decoupling here, causal decoupling of spatial points, they put forward this, well, it's a hypothesis really, is namely that time derivatives near the singularity should become much more important than spatial gradients. So that doesn't mean that things blow up at the singularity, but this just means that as you go to the singularity, the blow up of the time derivatives overwhelms the blow up of the spatial derivatives. And this means, if you sort of continue thinking about this, that effectively it's really like an effective, at the singularity, dimensional reduction to one dimension. That in some sense the system decomposes, so disintegrates, such that here you have totally isolated spatial points, and you have just a one-dimensional system at each point. And of course the idea was not to take this as a first approximation, and then sort of do a systematic expansion in spatial gradients, and thereby get a better understanding of the singularity, a more detailed than, say, you get from the Penrose-Hawking singularity theorems.
You can see the past singularity.
Pardon?
You can see the past singularity or future.
No, we're here talking about the past singularity. But if you, as you know, in Schwarzschild, the singularity is in the future, but it's also space-like. So whatever the behavior is, or what they said, should also apply to it. I mean, it gives you a more detailed description of what happens to you as you fall through the horizon and get squashed at the singularity. It tells you, well, the result is that you get squashed in a very interesting way. In a way that will sort of reveal this kind of structure. So this then fueled, I mean, at least, well, maybe I should also recall that all of this, the work we've done with Thibault and Marquenot and Axel Kleinschmidt, so this is spread over 10 or 12 years. But anyway, this sort of fueled the idea that we should think of this near singularity limit in the same way as one thinks about the high energy limit of gauge theories. Just like in the Standard Model, in order to see the symmetry, you have to go to high energies. Or in string theory, there were similar ideas connected with what's called the small tension limit. There's this idea, as you know perhaps, that string theory, as we learn it in school, is a spontaneously broken version of some other theory where the symmetries become apparent. This is also something that's nowadays being pursued with Vassiliev gauge theories and so on. Anyway, what we're doing is a sort of variant of this scheme, and then the idea would be that the full symmetry of the theory only becomes apparent at the singularity, and at the singularity, effectively, you have a dimensional reduction to one dimension, and it's only there that you would see this huge symmetry.
The alpha prime corrections to supergravity generally breaks these symmetries. And don't you usually expect supergravity to arise from alpha prime goes to 0 or the alpha prime goes to infinity limit?
Pardon?
I mean, you usually expect these, the pure supergravity theories with the continuous symmetry to arise from alpha prime goes to 0 rather than
Yes.
alpha prime goes to infinity limit. So you're here saying the opposite limit.
Well, I mean, I'm not committing myself to what finally the character of this symmetry is. You see, it could be it's broken to the discrete subgroup by stringy corrections, but even that is not clear how. I mean, in this context, you should not think about this too much in the way that you've been hearing about in string theory. So that was one element that goes into this, and the second is kind of, in order to motivate why we're interested in this. The second goes back to the way people thought about canonical quantum gravity some 50 years ago, the Wheeler-DeWitt approach to quantum gravity. So this is kind of old-fashioned, but we're sort of reconnecting to this old story. So this is 1962, roughly. And this was John Wheeler who sort of pushed this idea that the question is, what is the configuration space of quantum gravity, or moduli space of quantum gravity? What is this? Now he said, this is the space of 3 geometries. So he hypothesized that this is some very complicated space, namely the space of Riemannian metrics, spatial metrics divided by the diffeomorphism group. So the idea here is that when you do the canonical analysis of gravity, that the degrees of freedom are the spatial components of the metric, and then you evolve them forward in time by means of the Einstein equations. And then each hypersurface is characterized by some particular spatial geometry that changes or evolves as you move forward in time. Now I have no time to introduce canonical description of gravity. That's yet another lecture, so I just want to say that the dynamics of this is governed by the Wheeler-DeWitt Hamiltonian, alias the scalar constraint, or if you like, this G00 0 component of Einstein, of the Einstein field equations. And that has the following form. So here we have the Hamiltonian, or rather Hamiltonian density. Has the following form. This is the spatial metric. So as I told you here, things are characterized by the spatial metric and the associated conjugate momenta, which are related to the velocity. Velocities here are the extrinsic curvatures. But anyway, canonically, this system is characterized in this way, where these are spatial indices. And then what you find is the following. And here I take the liberty to use flat or curved indices, also here in this context, minus 1 over d minus 2 pi squared. And then we have minus square root g, Ricci, spatial Ricci. And then we may have matter terms which just indicate like this, e squared plus b squared. Okay, so this is, if you like, the momentum squared part. This thing is the potential. And it's important that you have a minus sign here. Comes with a minus sign. So potential is minus the spatial curvature, and this is matter contribution. Okay, so this is the, well, you also have canonical constraints and so on, but basically the dynamics of the system is encapsulated in this Hamiltonian, which you get from Einstein's theory. And so you can think now of classical gravity to start with as being dynamics that takes place on this manifold. Now this is infinite dimensional. It's kind of hard to wield or to control, but the basic features here are the following. So let me say this again. Any basic features? Let me first of all cosmological evolution can be thought of as motion, as the motion of a, of course, fictitious point particle on M. So if you could picture this, some manifold, and then you simply describe the evolution like this as a function of time. And of course there is no time here, but this is simply expression of the fact that there's no preferred time coordinate in general relativity. Theory is smart enough to know this and to take this into account. And then each point on this manifold corresponds to a full spatial geometry, as you see here. So each of these, the totality of the spatial geometry is mapped to a single point, and this point moves in this moduli space. No, I'll get to that. No, in general not in this context, but it will be in our context. So
Do you skip completely dependence on the special coordinate because you just when you put this kind of
well, as you know, we have this constraint at each spatial point.
at each special?
Yes, but for this reduction, we're going to pick one particular spatial point.
So for you doesn't matter the coordinate in principle can depend.
Well, an open question is now how to recover in our framework the spatial dependence. But let's get to that because part of this is still conjectural. So this is one important thing. The other important thing is that kinetic term here, which means this piece is indefinite. Well, of course, we also have an indefiniteness here because the spatial curvature can be either positive or negative. And this means that M is Lorentzian manifold. Okay? You see, this indefinite is crucial because previously I've been talking about the fact that gravity provides an infinite, unlimited source of energy. And it's simply the fact that this Hamiltonian, at the end of the day, has to be put equal to 0. And it just means you can borrow as much energy as you like from gravity and put it into matter. It's the thing that everyone dreams about, the bank account. There's no lower limit to withdrawals. Okay, so it's kinetic. And thirdly, now comes the question about the geodesic motion. If you write it in terms of curved indices, there appears a metric here, which is so-called Dewitt metric. So this is just a statement that the Dewitt metric is Lorentzian. But if you view it in this context, then if it was just this, then the motion would indeed be geodesic. So if a potential and no matter is constant, so this is just the constant term, and this other thing is absent, motion is geodesic. Okay, and then of course the Wheeler-DeWitt program was to simply take that Hamiltonian, perform canonical quantization, so replacing this by d by dg, and then apply it to some wave functional, which goes under the somewhat pompous name of wave function of the universe. So quantum theory, quantization, means that I introduce a wave functional whose arguments are spatial geometries. So it's a rather complicated, not function, but functional. Now, you also know, probably, that this whole program finally did not work. It ran into all kinds of difficulties because, I mean, to start with, this whole thing is mathematically ill-defined, and probably there is no way to make it well-defined. People nevertheless continue to use it. For example, in the context of quantum cosmology, when you do reductions to mini-superspace, they continue to work with this. But basically, problem, I mean, this whole Wheeler-Dewitt quantization program had basically ground to a halt in the early 80s because people just didn't know how to make sense out of this. So, I mean, what conclusion do you draw from this? One conclusion is that, well, maybe you're dealing with the wrong moduli space, and in any case, it's not quite clear what to put here, what the standard model or whatever. By P, I simply mean it's like a Schrödinger wave function, except that each point is a spatial geometry. So that's
which we can consider to be a point in M, right?
a point in M, yes. So it's really like the wave function lives on this space, and this was also the Wheeler's idea that somehow the wave function should smear over spatial geometries and thereby maybe even resolve singularities. So now let me say what the new aspect here is, or the proposal. The proposal is this, you conclude from that it's perhaps not quite the right moduli space, but we now go here to this and endow the moduli space with a group theoretical structure, namely well, there's a metric here in this kinetic term. This is called the Dewitt metric, or inverse Dewitt metric. And this is what I was saying here. It's indefinite. So, main claim, or claims, that we are making, partly results, but you should understand in what I'm telling you, the ratio of what we know to what we do not know is close to 0. This should be kept in mind. So don't ask me too hard questions. So, first result is that the kinetic term is the restriction of, well, rather than this sort of difficult to handle quantity, we claim that at least in the beginnings, this is the restriction of some bilinear or Casimir of invariant of some indefinite Moody algebra, well, which in our case will be E10. This then also comprises the matter degrees of freedom. And the indefinite here is important because the indefinite relates exactly to the fact that this kinetic term is indefinite. Well, you will get a 15-minute introduction to Moody algebras in a moment. Okay, so that's one thing. Second thing is that H, rewrite H such that, or reinterpret H such that cosmological evolution is mapped to null geodesic motion on the relevant coset space, which is it's of the type let me write it here, the relevant coset space, which is simply the space we get by straightforward extrapolation from supergravity. So you see a few things happen here. First of all, somehow we managed to turn part of this, at least, into, I said if you have this, then it's not a geodesic motion because you have a potential. But in order to turn it into this, we have to somehow exploit duality. And duality means somehow, roughly speaking, that the time derivative is mapped to the space derivative of a dual field, just like we learned for p-forms. So what you have to do is you have to convert this thing, this and this. Well, this is a kinetic term. This is a potential term. You use the dual magnetic field to express this as a kinetic term for the dual magnetic field, and thereby sort of lump this into this. And to some part, it can also, to a limited extent, can also be done to this, in such a way that the Hamiltonian now becomes basically just p squared. So that's the first thing to make it geodesic. And null, so that's geodesic, and null. Well, here I said if this is a constant, if you don't have this, because this is equal to 0, it will map it to a geodesic, which will be either time-like with respect to this Dewitt metric, or space-like, or null, depending on what this is. In our case, it comes out to be.
Assume that such a transformation exists.
Well, that's the claim. I'm not sure whether I have the time to prove it.
Why do you need a method? Because everything what you get will get anisotropic effects.
We're at one point. We worry about anisotropies, inhomogeneities later. Because you see the beginnings of inhomogeneous terms are contained in this, because there's a space derivative in here. And the whole BKL program was somehow to do an expansion, systematic in terms of time derivatives and then spatial gradients being smaller and smaller. In our case, we want to sort of reinterpret this whole thing, in fact, the full supergravity Hamiltonian in this group theoretical way. So I said this, but this so far we have just checked this at the beginning. It turns out that these algebras, unlike finite dimensional algebras, only admit one single invariant, Casimir invariant, namely the quadratic Casimir. Now we have a few more results, which I won't be able to talk about here. There are other constraints. One of them has to do with, there are diffeomorphism constraints, Gauss constraints, and so on. These we have been able to associate with null roots. I will say what this is in a moment. So constraints. And finally fermions. And for this, you have not to go to some hypothetical super extension of this group, which doesn't exist or does not appear to exist, but as irreps of this compact subgroup. So it's exactly like in higher dimensions, where the fermions don't transform under the hidden symmetry group, but under the maximal compact subgroup. So this is exactly like in n equals 8 supergravity. And then you can rewrite, for example, the Ravita-Schwinger equation, which I didn't write out, but it's something, 11-dimensional supergravity, something more complicated, as a kind of KE10 covariant Dirac equation. So there's now lots of, quite a body of results, which I have no time to talk about. Rather, so I have to be careful with my time, I have to now to tell you what these algebras are. Now it's one thing to say, well, E8, E9, E10, That's simple counting argument. But what is this? So I've saved some time by giving you some basics of the theory of Katz-Moody algebras, which were in this form invented in 1968 by Katz and Moody. And the theory of Katz-Moody algebras is basically about constructing Lie algebras from basic building blocks. And the basic building blocks are very simple. The basic building blocks are SL2 algebras, which are glued together by means of a Dynkin diagram. So one starts out with generators, EFH, that's what they call the mathematical literature. And you can think of them being like J plus, J minus, and J3 in standard SL2. So that's one building block. The second building block is Cartan matrix, which is matrix with certain properties, which you can look up on page 1 of Victor Katz's book on infinite dimensional Lie algebras. And then there are certain relations which have been formulated in this form in the 50s by Chevalier, French mathematician, and also Serre. So and here they are. So these are the relations that are obeyed by these generators. By the way, physicists talk about generators when they mean any kind of the algebra element. Here, with generators, only one really means the building blocks, the basic SL2 generators. And then they commute like this. This simply says that J3 with J plus is J plus, because the Cartan matrix is such that it has +2 on the diagonal. This is the lowering operator, E is the raising, F is the lowering operator. And the H's span the Cartan subalgebra. So it's really like in quantum mechanics, we have a system of operators. We restrict to a maximal commuting set of observables. That's what the H's are. And the rest of the algebra, just finding commuting elements is not enough. The rest of the algebra has to be diagonalizable with respect to the action of these H's. And this is what you see here. And furthermore, J plus with J minus gives this. By the way, summation convention is suspended here. And then there's an important relation, multilinear commutator, that says, because the matrix elements are, off-diagonal matrix elements are negative integers, you have a certain multiple commutator that must vanish, and that multiple commutator, its order, is determined by what's here. So for example, if there's a 0 here in Aij, it just means that these two things commute. So simple example, take A2 following Cartan matrix, and then here you get E1, E2, you get E1, E2, and that's it. And same for F and H. So, and if you take any further commutator, then you will get 0. Here we turn this around. We say that we abstractly define the Lie algebra in this way. And that's the algebra then. So SL2, SL3 is simply has dimension 8 because I get 3 like this. I get 3 from the F's plus 2 Cartan subalgebra elements. Well, exercise, do this for A1 was, well, called A11, which the matrix is like this. Okay, and the algebra you get in this case is SL2 hat. It's already infinite dimensional with a central extension. So nice little thing to do.
Why it's infinite dimensional?
Well, it just means that when you use this prescription, sorry, I said that the algebra is of course now defined by taking all multiple commutators subject to these relations.
Subject to this relation.
Yes, so that means that, you know, here in SL2, SL3, this
So you will get generic.
this is equal to 0, but here, because I've increased this by 1, this is a new element of the algebra. And then when you try to work through it, you will realize that actually you need an infinite number of multiple commutators. And in fact, difficult exercise, really unsolved problem. Do this for well, you can look at, well, one could to the beginnings. This is actually when the algebra explodes in your face. Well, this is already infinite dimensional, but this is just infinitesimally infinite dimensional in comparison to this. You know, it is a little bit counterintuitive because you think, well, what difference does it make what I put here? 1 or 2, you know, doesn't make such a big difference. It makes a huge difference. It makes all the difference.
Sorry, what's the general condition you put on AIK?
Well, I'm just saying that. Just getting to this. I still have half an hour. So, before I come to the classification, let me just say 3 things. Namely, you know, what's the use of this? Why do these things in this funny way? Because we anyhow know what the finite dimensional algebras are. They were classified by Cartan and Killing already more than 100 years ago. Why go through this? And actually, Chevalier, when he invented this, he was interested in defining Lie algebras over finite fields, and then he needed a basis with integer structure constants. And Katz and Moody, their generalization depends on something else. Namely, they observed, or they knew, that the finite dimensional Lie algebras were all such that A is a positive definite matrix. If you go through the list of in the group theory books, go through the list of Cartan matrices of finite dimensional Lie algebras, all of them are positive definite. So they said, so for Chevalier and these people, this was good enough for what they wanted to do. But Katz and Moody, of course, were looking for more general algebras. And then they said, let's just drop this requirement and see what happens. And out of this comes the classification. So classification, which is such that if it's, we can now turn it around. If you start with any Cartan matrix, satisfying the general properties of a Cartan matrix, then you will just recover the old result. Now the next case is when RA is positive semi-definite and has a 0 eigenvalue, then you get what's called affine. Affine, that's Moody algebra. Okay? Well, affine Katz Moody algebras are current algebras. That what you know from string theory, you just take the Lie algebra element and append an integer index, or turn this into a current that lives on the circle, or depends on one complex variable. And so this is when you have TA generators. You simply affinize them by putting an index here, where M runs over all integers. Okay? And now you see this does have a 0 eigenvalue, and therefore it falls into this category. And finally, we have A is indefinite, and in that case, we don't know, or very little is known. When Victor Katz, he was awarded the Wigner Medal, group theory Wigner Medal, and of course for his work on Katz-Moody algebras. And he started out by his acceptance speech by saying the theory of Kac-Moody algebras is a disaster. Why is it a disaster? Because, well, 50 years later, almost, we still don't know what this is. We have fairly good understanding what this is, because here we have a concrete realization in terms of current algebra. Of course, this is known, but here there's no such thing as a concrete realization. Now, in order to get to the more physical questions, let me just say one other thing about Kac-Moody algebra theory is that it has, even if they're infinite dimensional, they share certain properties with matrix algebras. So in particular, we have what's called Tricomposition. So it means that the algebra can be decomposed into lower triangular part. So think of this like matrices with entries only in lower triangular half, Cartan subalgebra plus upper triangular. Okay, that is important for computability because I've already mentioned in one of the previous lectures that when looking at the field point, we make use of a triangular gauge, or the Iwasawa decomposition, if you like. Now here, this is absolutely crucial because finite dimensional matrices, we can also choose other configurations where the matrix is not upper triangular, but here it's absolutely essential in order to be able to make any kind of calculation. You know, I said that we're talking the configuration space will be this divided by the maximal compact subgroup. And in practice, it means that when we do a calculation, we can go to a gauge where it's just like this. And then it sort of only goes in one direction, and it remains controllable. Secondly, there's an invariant bilinear form, which generalizes the trace, which in the finite dimensional case just reduces to the trace. So even though the algebra is infinite dimensional, there's a scalar product can be defined in this way by means of these generators, the invariants, and these relations. And this is important if you want to formulate an action. Because when we write down sigma model actions, we need some kind of invariant trace form. And finally, the thing admits a root space decomposition. So it's just like roots for finite dimensional Lie algebras, except that because we're indefinite, the roots now live in the Lorentzian space, not in the Euclidean. So the roots are now come with in three different varieties. They can be real roots, what's called real roots, or space-like. That's what you have in standard Lie algebra theory. They can be null, affine roots, null roots. That is this case. And here they can be indefinite. So this is one way to... There's another analogy with the string theory. You cannot think of these roots as being tachyonic, like tachyon momenta. This is when you add the photon. Photon has light-like momentum. And this is like adding all the massive states of the string. This sort of makes plausible, at least where this explosion comes from. So this compared to this, this is just like having a tachyon. This is when you add a photon to the tachyon, and here you go to the full set of excited massive states of the string. So, how does this now connect to what we... No, it's just an analogy. Then I would now have to go into vertex operator algebras. That's a separate lecture, a separate set of lectures, actually. So, now out of this classification, now when you go admit this, of course, then you can do essentially anything. There's no upper limit. In this case, you have a finite list. In this case, you also have a finite list, which you can give, which you can find in Katz's book. it's essentially just the affinizations of the known finite dimensional Lie algebras, possibly some twist. But otherwise, this is also classified. But here, it's just like opening Pandora's box, because now you can write down any Cartan matrices, as long if you allow it to become indefinite, and therefore one introduces a further criterion. Hyperbolic means indefinite, definite, and any regular subalgebra. By regular here I mean algebra that's obtained by removing one node from the Dynkin diagram is either affine or finite. So the Dynkin diagram should be such, or the Cartan matrix should be such, that when you remove any point on the Dynkin diagram, you'd either here or here. Now that's very restrictive, because then it follows that the rank must be of G of A, meaning dimension of Cartan subalgebra less than or equal to 10. So if you now you can classify these things, and there's something called E10, which is simply the following Dynkin diagram: 4, 5, 6, 7, 8, 9. That's one. There's another one called DE10, and this is obtained by putting the node like this. And there are two more, which are, let me just write one, E10, which are not simply laced, meaning that you have roots of different lengths. Well, you will see in a moment, it somehow fits precisely what we know from supergravity. You see, this is the amazing thing. There's this mathematical theory that comes basically from physicists' point, out of the point of view, out of the blue. But it turns out that that this is really related to, well, M theory in some sense, or D equals 11, supergravity. Well, that's already what you got from what I showed you at the beginning. If you simply extend the E counting down to low dimensions, this will be related to type 1 gravity, supergravity. That's half maximal, and this will be basically related to type 1 plus vector multiplets. Okay, so one way to see this, and here the hyperbolicity criterion is important.
C10
has the other arrow in the other way, but there we don't know. Or is there some physical system with a CE10? Not quite sure. Not an open question. Anyway, what I want to emphasize here is that on the one hand, we've been doing supergravity, maximal or half maximal. On the other side, there's this classification of hyperbolic Kac-Moody algebras. The maximum rank algebras are somehow in correspondence with maximally supersymmetric theories. So, now how do you see that this is really related to something we know, or which I've already told you about? And this is this has to do with the fact, well, here the hyperbolicity comes in conveniently, because now I said that these algebras are hugely infinite dimensional, not just infinite dimensional. So, you know, how do we approach this kind of construction? And one way to do it, if you like, the poor man's way of approaching the subject, this is not what the mathematicians would do, by the way, is what we call level decomposition. And this means the following. Then we call this root alpha 0, the one that's associated with this node. And let me call this 1, 2, 3, 4, up to 9. Okay. One thing you can do is you can take, given any root of the algebra, and there will be certain Lie algebra elements associated with, you can take that root and decompose it as follows into basis of these other roots. Okay, so that means you split off this root and give it a special status. And then, and here's the hyperbolicity is important, because if you take this away, you're just left with a finite dimensional algebra. It's just SL10, or rather GL10 if you take the Cartan subalgebra generator from here. So that means if I do this kind of decomposition, look at the corresponding elements, if I just act with an element of SL10, this SL10 subalgebra, it will leave this decomposition of the Lie algebra invariant. So this means really I'm decomposing E10, I'm writing it as a union of stacks in some sense of SL10 or GL10 really irreps. So this is one way to approach, if you don't, to get a good feeling for exceptional groups, one way to do is you take the exceptional group and decompose it into representations of some subgroup that you know and understand better. Like for example E8 in terms of its SO16 is just the adjoint of SO16 plus a spinor. So that's something one understands. So this is similar. And what you get then is the following. For L equals 0, you just get the GL10 subalgebra. That's easy.
L and M are positive?
Yes, sorry. L, M, I are either all. We talk about positive, negative roots. They're all positive or non-negative. At Lx1, what you find in terms of SL10 or GL10 representation is just this thing, which you've seen before. L2, 1, 2, 3, 4, 5, 6 form. And finally, for L equals 3, we find for the first time a mixed representation, which looks like this. And now you recognize that this is something I've talked about before. Because this, what is hidden in here, if I think about the... by the way, for the negative L's, you will have a similar tower of representations, the conjugate representations. This is just related to the spatial part of the Vielbein. This is the 3 form which we encounter in supergravity. 3 form. This is the dual 6 form. And this thing finally is what I introduced as the dual graviton. Okay? So you see emerge out of this analysis. I've never used the word supersymmetry. I've not used supersymmetry anywhere in this argument. Nevertheless, this algebra, by making this decomposition, knows exactly about the field content that appears in maximal supergravity. And incidentally, you can do a similar analysis with not giving this point a special status, but if you take this one, this will give you what's called M2A, the M2A multiplet. In M2A, the hidden symmetry is SO9,9. This is what you get by reducing the T duality that you get by going from to one dimension. And when you analyze this, in the same way, you will just find the corresponding bosonic multiplet of type 2A, including the Romans mass term. And finally, you might also single out this term, this node, and then you get what's called 2B, because here you see the SL2 of type 2B supergravity. times an SL8. And again, when you do these decompositions, from this you will recover the bosonic parts of the 2B supermultiplet in 10 dimensions. So this is just to tell you that the E10 encompasses all these cases because it contains, depending on how you look at it, it contains the complete information about the bosonic spectrum of the supergravity series. Well, I'm just going to say this. Now, this decomposition is, let me see, what happens. So, L less than 3 is enough for En, n less than or equal to 8, because we know that the highest number of times this exceptional root can appear in the decomposition of any root is 3. So we just have these 3. And if you decompose it for E8, you just take away these 2 points. Then you have a GL8. And then you see that this is just gives you the GL8 decomposition of E8. So that's fine. For L for E9, what you find is that this pattern repeats an infinite number of times. So you get an infinite number. So you keep going. It's infinite dimensional now, but so at level, say level 4, you find another one of those. Level 5, another one of those, and so ad infinitum. And that's exactly the infinite reduplication of L less than or equal to 3 spectrum. And that's, of course, exactly what you expect, because it just means I take the EA generators and I just give them an integer label. So that precisely, this kind of analysis precisely recovers the current algebra description. I can give you references where you can read about this, where this is done in all gory detail.
The relation between L and N is simple?
It's not completely obvious, because, I mean, it's a sort of, you have to work for a week or so in order to make, but it's made explicit in our paper, so it's completely explicit. You somehow have to, I mean, if you think about affine levels, actually, here, they're somehow a little bit shifted, but, in a way that can be understood. For E10, there's no such list available, so we put it, or my student rather, Fischbacher, it's very good with computers, put it on the computer, and you find that up to 28, the number of irreps is on the order of 4.5 times 10 to the 9. It's just people.
What does he have explicit?
Well, what if explicit is all the representation labels of SL10, meaning all the Young tableaus. Yeah, this is done using Dynkin labeling, but you can translate it into this kind of language. And then you see, as you keep going, that about any SL10 Young tableau will appear in this decomposition. So I'm just emphasizing this, again, to make the point, because, as I said, you just keep adding one row and column to the Cartan matrix, so it doesn't seem like such a big deal. But here you see it, and it's exactly this fact. Here the Cartan matrix becomes has a 0 eigenvalue, so you can still handle it, and here becomes indefinite. And these things which you see appearing here in a sort of root space way of looking at it is that now in root space you have the Euclidean, so you have a hyperboloid, a mass hyperboloid, which looks like this. And the real roots, the ones you can handle, are the ones that are out here. Okay. Sorry, I'm saying this wrong. I should draw a light cone. Sorry, not a mass shell. So here I have a light cone in root space. So here's a time-like direction. Time-like. So the real roots, the tachyonic roots, they're like this. There are now infinitely many of them. Okay, so that's fine. And then you have the affine null roots. They sit here. Oh, wow, the null roots. One of them is affine. But actually in this algebra you will find infinitely many. I mean, in some sense the whole light cone will now be covered by such roots. And finally you have the roots, the time-like roots. These are space-like, that sit in here. And this is really where the thing becomes complicated. It's a little bit like the string spectrum by analogy. Tachyons are simple, they're just scalars. The photons are the null roots. And now here have the massive string states, and it's, as you know, massive string states come with exponentially increasing multiplicities. And exactly the same thing happens here. And this shows you where this comes from. So this, just to give you an impression of the monstrous complexity, because somehow people think, well, E10, E8, E9, E10, it's just this bigger Cartan matrix. In some sense also the Weil group. The Weil group is now a subgroup of, discrete subgroup of the Lorentz group in 10 dimensions, but that still can be handled. But you know, if you think about this the way a physicist would think about, it just seems impossible because, you know, as a physicist, if I tell you as a physicist I have this symmetry, then you will ask me, okay, give me the list of Lie algebra generators and give me a list of structure constants, and then I know what the algebra is. Here, even the problem of listing or even only counting the number of Lie algebra elements as a function of length as you move into the light cone is very difficult. Basically, I think some great mathematicians have actually given up on this. But, well, I think it has a little bit to do with the fact because we physicists know so little, and therefore we're not afraid of, you know, doing such things. Anyway, so you would have to give a list of the generators, and just writing down a list of the corresponding structure constant is impossibly difficult. And worse yet, even if you succeed in doing this, you can be sure that as you move on, it will get even more complicated. So unlike affine, where so the pattern sort of repeats, same pattern, repeats an infinite number of times, here it gets completely out of hand.
Yeah, 5 minutes plus.
5 minutes plus. So, let me now just say in a few words what, I mean, just.
Question, if you choose a different subalgebra,
Yes?
can you repeat the same analysis?
Yes, you can, for example, if you want to understand decomposition of n equals 8 supergravity, then you'd take this node, then you have a spatial, we think about spatial coordinates, so it's SL3, so you take this away, and then you decompose, and that will give you the representations, E7, that appear in n equals 8 supergravity, but it will also give you, as you keep going, it will also give you the higher order tensors that I talked about last time. So the 912 will be associated with the 2 form, and for the 3 form you will, well, you know, you just keep going, and then you will recover this tensor hierarchy at the bottom of this decomposition, the tensor hierarchy which I mentioned in my last talk. Okay, so let me just in 3 minutes, because I haven't really gotten yet to what I wanted to say, but so what we do in order to come back to this analogy, or relation which I mentioned, or the claims which I stated at the beginning, where I said that we can map at least part of the supergravity to this E10 sigma model. So what you do, you simply assume formally that you have a element of the coset space like this, and then you simply formally, and this is where you need the triangular decomposition, you formally write this as a sum over level. In principle, it goes from L0 to infinity. Here use the fact that the gauge symmetry, here use the triangular decomposition in order to get rid of the negative levels. And then here you have some set of fields times some set of generators, one for each level. So by the time this L reaches 28, you already have quite a lot of things to deal with. But anyway, we make such a formal ansatz. And then you use the same kind of technology that I showed you last time. You look at the Cartan form. You write it as Q and P, where this is in KE10, the compact subalgebra, and this is KE10 orthogonal complement. And then, okay, so then we have to make certain truncations, but what turns out when you restrict L to L less than or equal to 3, meaning to these fields, which we kind of understand, the dual graviton, the sigma model equations can be mapped to the supergravity equation. So here we have an expansion in level or height of the root, and this gets mapped to an expansion, a BKL type expansion in spatial gradients. Yes, right. So how do we get the action? That's a nice thing. So you have this decomposition, as I said, and then the action is simply taken to be proportional to the bilinear form of this PT. So it's the unique action you can write down. From the Lie algebra theories, there's only one thing you can write down, and it's this action. And from this action, you get just the usual sigma model equations using this decomposition. And then we have to truncate here we truncate to level 3, or rather height alpha less than 29. That's the root height. And here we truncate to spatial gradients, first or second. We truncate away second order spatial gradients. And then you need a dictionary to relate the supergravity quantities to the sigma model quantities. And then you can show or verify the claim I stated at the beginning, that there's a one-to-one correspondence between the sigma model equations and the truncated supergravity equations. And furthermore, because this is also essentially going to give the Hamiltonian constraint, the thing, the sigma model equation tells you that it moves on a geodesic on this infinite dimensional manifold, and then the Hamiltonian constraint tells you it's a null geodesic motion. And for this is crucial that you somehow have converted spatial gradients into time derivatives of dual fields. Well, pardon? Fermions. Okay, let me just, in 1 minute. So here we have Q of t plus P of t. And in the beginning we just looked at the bosonic equations of motion, but when you look at the fermionic equations of motion, you have to construct a representation of KE10, which strangely enough turns out to be finite dimensional. It's not faithful. And then you can reproduce a non-trivial part, not the complete, because there are spatial gradients here, of the Rarita-Schwinger equation in terms of a covariant derivative, which is covariantized with respect to this k of E10. And do you remember in my first lecture when I stated that delta psi is somehow d plus omega plus f on epsilon? We now, with this technology, this can be somehow converted to d plus q of t, using, first of all, the expansion here, and secondly, using the dictionary that relates these quantities to the supergravity quantities. So in some sense, after a lot of work, you realize that this expression, which sort of looks, it comes about, in some sense, it comes about from supersymmetry. This was how it was derived by Kremer-Julia-Scherk. It now turns out to be entirely group theoretically determined by this. So I think I should stop here. It's anyway, I didn't hope to be able to explain everything, but I just hope to be able to give you a flavor of this. And let me repeat what I said. We've, I think we've done a lot of work and discovered many interesting things, but the ratio of what we know to what we don't know is very close to zero. It's epsilon. Any epsilon, take it as small as you like. Okay, thank you.
This is the second full-length lecture. You will still have cosmological billiards, or this is the last one?
This is the last lecture.
Okay.
Well, I was asked to lecture about supergravity, not about cosmological billiards. This would have been a different line of attack, but...
Okay, so in view of the time, I think we just have a 15-minute break. Let's thank Hermann again for the whole series of lectures.
Thank you.
And we have a 15-minute break.